Okay, then welcome everybody. My name is Rafael Santos. I'm going to be the president, the manager of this evaluation committee of the final presentation of Igor Kolesnikov thesis. That's a PhD thesis. The title is Unveiling Galaxy Morphology Through an Unsupervised and Supervised Hybrid Approach. The members of the committee is myself, Rafael Santos, Dr. Reinaldo Carvalho, Reinaldo Rosa, and Celso Mendes, that are Igor's advisors. Then Dr. Gilberto Queiroz, and as a member from our organic program, Dr. Christopher Concelis and Dr. Ariana Cortezes as members from outside INPE. Igor, you have around 45 to 50 minutes. We are not going to press you too much on that, but if you pass 50 minutes, I'm going to start making justice. And you can present whenever you want. After the presentation, we are going to have the questioning, and after that, the deliberation. So welcome everybody. Thanks for participating on this committee. And Igor, you can start whenever you want.
Okay, thank you. Thank you so much, everyone, for being here. Okay, just a check. Can everybody see my first slide of presentation?
Yes.
Yes, perfect. Okay, so good morning, everyone. My name is Igor, and I will present to you my research thesis and what it contained. If I would have 3 minutes to present thesis, I would do it something like this. Basically, we had two main steps of whole research. First one was pipeline refinement, and second one was hybrid methodology. During pipeline refinement, we revised Cy-Morph package that we received from previous PhD student who finished his PhD in 2020. We decoupled, revised cleaning, segmentation, metrics, everything, increased performance, reliability, and prepared data for our future research. So it's basically took us around 2 years. And during hybrid methodology, we defined the hybrid method as we saw it, adjusted a lot of parameters, testing, evaluation, well, as always is. And finally, we extended its applicability to different data sources. As to results, results for the first stage was robust cleaning and segmentation routines, fast, reproducible, and reliable metric calculation, because it's important to have this as a first stage because our hybrid methodology is based on morphological metrics. So we need to be sure that they are working as they should. And with hybrid methodology, it's just 2 lines. We get around 95% of overall accuracy with unsupervised accuracy and around 88% with hybrid accuracy. Why hybrid accuracy is lower? Because here we're testing on almost 1 million galaxies. So the scale is that big. And well, there is several more details that I will comment later. Basically, this was the thesis. And now we are going into details. Oh, before, some presentations that we did during the thesis and main publications that we done by the end of the last year, presenting this method in MNRAS paper. Right, now starting with the main presentation. I would say that astronomy is quite a complicated area of science because we cannot take galaxy from the sky, put it below the microscope, maybe take a part of it, pick it with a needle, take it to the lab. We cannot do it. So everything that remains to us is just observation. But even with observation, a lot of processes that govern universe are extremely time-consuming. So we end up looking at something so distant that seems almost immutable. And that's why we need to come up with different tools and techniques that will help us to extract more information from observations that we have. And here where comes morphology and morphological metrics. Morphology by itself is not new. And it's already in 1923 with Edwin Hubble and famous Hubble fork, where he tried to catalogize galaxies between different groups. There's a lot of them, but here we only will be focusing on spirals and ellipticals, where ellipticals characterized by bright center and smooth flux decrease closer to the borders, and Spiral galaxies usually characterized by not so bright, but still noticeable center and spiral arms around. Just a simplification for to give a notice to everyone. But this field got a lot more attention with the publication of papers of Christopher Consolis in 2000, 2003, where he argued that CAS metrics, CAS system that he presented, correlate with key modes of galaxy evolution, such as star formation, merging activity. Then Jennifer Lotz in 2004 noted that high values of Gini and M20 usually are indicatives of recent or ongoing mergers of the galaxies. And finally, Paul Barkey, who defended his thesis here at IMPI 4 years ago, he did a very, very curious experiment where he used morphological metrics as a base for machine learning algorithm training. And he was able to get high accuracy using algorithms trained on metrics and ones that he used images. So it was really good results showing that metrics do have potential to be used as a base for training. So given this introduction, we can conclude that metrics are closely related to physics of the galaxies, and they provide valuable information about evolution and environment. And that's why, having these two important notions, we invested a good amount of time into investigating and comparing metrics that we had available at hand. So we started with CAS, and it's well spread and well used system. But when we focused on morphological separation, CAS did not always provide a significant results. That's why we invested time into compiling our own system. Of course, all these metrics not new, but we combined them into egg system, contained entropy, Gini, and gradient pattern analysis, and all of them are focused on morphological separation. So here's in details about each of them, starting with the entropy. Basically, entropy measures heterogeneity of flux distribution on the profile of the galaxy. It's easier to see on the example. So let's imagine this is our galaxy, simulation of the galaxy, brightest pixel in the center, and their smooth decrease closer to the borders. If we will unravel this galaxy into 1D vector and plot it on the histogram, the wideness of the histogram will define this heterogeneity. So how varied the pixel distribution on the galaxy profile is. And here is real data. So blue line is a spiral galaxy and red line is elliptical one, just one galaxy for each class. We can see that spiral has wider distribution and it has more counts across all the flux range with x, which is x-axis, than elliptical. And on top, you can see that elliptical galaxy has value of entropy of 0.3 and spiral 0.7. So there is differentiation, but it's just one galaxy for each class. So if we run 50,000 galaxies and calculate entropy for each of them, we can see this distribution where indeed majority of spiral galaxies will have higher values of entropy, while majority of elliptical will have lower. Here we have A0. This is our kind of simple metric of quantifying how well separation is working. So it is just calculation of area of overlap, because this histogram is normalized by area, so both of them are 1, and it's easy to calculate the area of overlap. And for us, when area of overlap is lower, better separation is. We will be using this this A0 metric across all next demonstrations. Right, going to the Gini. Gini as well measures flux distribution, but what it does is tries to quantify how concentrated or distributed flux is. It came from economy, and in economy, when you have low values of Gini, you have wells concentrated in small amount of people, and when you have high values of Gini, wealth is concentrated in high amount of distributed between a lot of people. In astronomy, it's similar, but instead of wells, we have flux. So in case of Gini, I'm sorry, it was inverse. So in case of Gini, high values of Gini will demonstrate a concentration of flux. This is red distribution of elliptical galaxies, and good distribution of flux all across the galaxy profile will be demonstrated more characteristics for the spiral galaxies, which is blue distribution. And finally, G2. I would say this is more involved metric because there are several steps, and I will try to go through them. Basically, we try to quantify the disturbance in the gradient field of the galaxy. So here we have a galaxy, original picture of it, and gradient field of this galaxy. How does it work? So we are starting with the image of the galaxy, and we need to produce gradient field. To produce it, we will go pixel by pixel on the galaxy, and based on the flux intensity of 9 neighbors, we will assign a vector and phase for this pixel. So basically, for this galaxy, we will receive something like this. This is real data, and we can see how well gradient field captures spiral pattern of this galaxy. Now, having this gradient field, we will go and compare all the pairs of the vectors between them. And if we will have same strengths and opposite direction, these vectors will be called symmetrical, and they will cancel out because they are not interesting to us. But if we will find two vectors that not exactly opposite or have different strengths, we will preserve them, and they will contribute to G2 value. Why it's important? Because here, this is our original gradient field, and next slide will be one when we remove all the symmetrical vectors, like this. And what is important, that even after removing all of them, we still see spiral pattern. This is our disturbance. And what is more remarkable is when we compare gradient field of elliptical galaxy and spiral one. So spiral on top, elliptical in the bottom. Original field of both of the galaxies and asymmetrical field without all the symmetrical pixels. You can see how few pixels remained in the elliptical galaxy. So basically, this is what expected because the flux distribution is pretty smooth. That's why in the end, we will have majority of the galaxies from same sample of 50,000 galaxies that we are using will have high values of G2, while majority of ellipticals will have small values of G2, providing very good morphological separation. So just making a summary of this comparison, in light of greater morphological separation, we shall continue with the X system because across of 3 metrics, we are getting better separation than CAS system, because in CAS, asymmetry and smoothness unfortunately have distributions almost one on top of the other. And right, a few words about processing pipeline, because it's important how we calculate the metrics before we indeed calculate them. We're starting with cleaning of the image, because this is what we get from the telescope. We need to remove secondary sources. They could cause disturbance in the calculation of the metrics, so we remove them. Then we segment the image, so we attribute 1 to all pixels that belong to the galaxy and 0 to ones that do not belong. And finally, we overlay this segmented mask on top of the cleaned image, and we receive our segmented image, where in the pixels that belong to the galaxy, we have real counts, and all around is 0. It's easier to say than to do this identification of which pixels belong to the galaxy, because we can cut too narrow and we will lose a lot of information from the galaxy. We can cut too wide and we will include a lot of sky from the around of the galaxy, which will contribute with the noise. How can we do it exactly, precisely around the galaxy to take only pixels that belong indeed to the galaxy? Well, that's why we invested a good amount of time in this process, and we found that segmentation method presented in Jennifer Slott's paper from 2004 works the best in our case. And moreover, it uses pixel attribution is tied to Petrosian radius of the galaxy. And knowing that Petrosian radius is resistant to redshift dimming, so this segmentation method, it will work equally good in the local universe, in the low redshift, and in the with the galaxies with high redshift, which is important for our future testing. And a few comments about computational performance, because we did revision, and along with revision, we did a computational optimization. So basically, the code that we received from Paolo Barchi 4 years ago, to process 1,000 galaxies on this machine, we needed around 1,000 seconds, so 1925 seconds. After all optimizations to achieve same results, we got almost 10-fold performance improvement. And it's important because we have a lot of data, and processing it faster really helps in speeding up the research. Right, so recapitulating, we already know that metrics related to physics of the galaxies, they provide valuable information. And now we can add that they are objective numeric descriptors. So it's just a single number that will characterize a given flux distribution of the galaxy. And they are fast and relatively easy to get. Before we will delve in the method itself, we need to see how morphological classification is done currently, the most common way in the literature. So most common, from what we see, most common way is using citizen science projects like Galaxy Zoo that we using as a testing catalog in this research. So how it works? You get your data set that you want to classify. You invite a lot of volunteers that will classify this object with little training. You prepare a graphical interface, show them the images, and they will be clicking depending on the type of the galaxies that they see. And for example, in Galaxy Zoo 1, they had almost 70,000 volunteers and almost 3 million classifications. So basically, as a final result, you will receive a table of objects and corresponding class that was most commonly agreed between all the classification. And you can use this table, you prepare your images to train a CNN model that you will reapply on the similar data, and you can scale up the morphological classification. So basically, this is the most common way. But the thing is, when we look at the galaxy, we try to segment it. We try to identify parts and features that will help us understand and classify which galaxy it is. So for example, here we can see a bright center of the galaxy, main body of the galaxy, and spiral arm of this galaxy. So we kind of know that this is spiral galaxy. It's pretty clear, right? But for the matrix, it's not necessary at all, because for matrix, it's just they see a galaxy as a 2D array of pixels where each pixel will contain some value of flux, and each metric will try to quantify this depending on its nature. So G2 will try to see disturbance, entropy will try to see heterogeneity of distribution of the flux, and so on. Both of these approaches work equally well when you look at the galaxies in local universe. So bright, big galaxies, when you can identify spiral arms, when you can see a smooth decrease of the flux in case of elliptical one. But the issue starts to arise when you look at something like this. This galaxy is from redshift around 2, and it's not exactly clear which features can you identify here to be able to classify this galaxy. And well, you might be surprised, but still in the left we have a disk, which is bigger. It's more like umbrella term that includes spirals as well. And in the right, we have spheroids, which is umbrella term that includes elliptical. But it's not clear which one is which. And sometimes it would be even mood dependent. The classification could be mood dependent. So given these challenges in high Z, where going higher than redshift 1, we start to lose the distinguishing features that human eye can easily identify. And moreover, when we are transitioning to the disk and spheroid plane, features not only not obvious, but sometimes ambiguous, and it's not clear how to classify them for human eye. But for metrics, it's still 2D array, and there is still a distribution that can be quantified. Of course, you cannot count to get a reliable quantification when you have only 3 pixels. You still need to have a good resolution of your telescope. But we argue that metrics can be an alternative to human eye classification in cases where bias from human eye will be higher. That's why we presenting this hybrid classification method, which is based on morphological metrics. And in a nutshell, if we would summarize the core steps, it basically starts with data preprocessing, where we clean, segment images, calculate metrics for each of them, clustering, unsupervised labeling, CNN training, and CNN usage. Last 2 steps, I would say they would be the same as if we took the catalog from Galaxy Zoo, because you take from Galaxy Zoo and you train your model. So in our case, step 4, unsupervised labeling, will provide this catalog without need of human intervention. Right, what we are using for the testing and the comparison. So we are using data from Dominguez Sanchez paper, 2018. It's data from SDSS telescope, local universe, so up to redshift 0.3, pretty bright galaxies. And the best of it, there is a lot of them, more than 500,000, and they all have T-type. T-type calculated by the formula from Mirt paper 2015. And from this sample, because we don't need all 600,000 galaxies, we just need a fraction. So we randomly select 36,000, and we will use them to prepare our method, because we need to go through the whole process of comparison to be able to apply it. So 36,000 seems like a reasonable amount. So we select it randomly from the whole sample. And with this 36,000, we start with the data preparation. So we clean, segment images, then we calculate metrics for each of the 36,000 of the galaxies. So each galaxy will receive a set of 3 metrics. This is basically our table after the metric calculation. So you have a galaxy and 3 metrics for each of them. And then we are going to unsupervised clustering. For this, we are using some algorithm and the implementation of Sombrero. Basically, some algorithm, you can imagine it as a blanket. When you throw it on your data, this blanket will be stretched around clusters that will be homogeneous within these clusters, but different from all other clusters. And this is how, if we will bring the analogy, the some algorithms work. And Sombrero, it's a package that it's not our development, it's already existed, written in R, that simply provides a very good environment with a lot of functions and tools that we can use to harness the ability of SOM to clusterize the data. So basically, as I was saying, we have this table. We will feed it to the SOM, to the Sombrero. Sombrero will prepare a grid. So here we have a grid 4 by 4 with total 16 clusters, and galaxy will be distributed between these clusters. But as you remember, it's like a blanket that will be stretched. So galaxies that have more prominent differentiation of metrics will be stretched as far as possible closer to the corners. So we will focus in the 2 groups of clusters 3, 4, and 8, and clusters 9, 13, and 14. For now, of course, there is a lot of clusters in the middle, but we will ignore them because they are not interesting for us, and later I will demonstrate why. So these two groups, if we would look with detail, we can see that clusters 3, 4, and 8 will, in majority of them, will have higher values of entropy, lower Gini, and higher G2. This indicates for us, as we saw previously, spiral galaxies. So we can assume that majority of the galaxies that are in these clusters are spirals, purely based on metrics. Same thing we can say about 9, 13, and 14. The image is opposite, so most probably there is majority of the elliptical galaxies. Knowing type of the galaxies that are there beforehand, because we are testing this method, we can try to verify this. So plotting the content of these clusters, we can see where blue is a spiral, elliptical is a red. We can see that indeed, for example, cluster 3 has almost 99% of the galaxies that within this cluster are spiral. Same thing we can say about cluster 9. Majority of the galaxies are elliptical. So metrics are able to capture this, and Sombrero is able to use this information from the metrics to separate these galaxies between different clusters without any previous knowledge of the label of the galaxy. So basically, just an image why middle clusters are not interesting. You can see there is a lot of mix match of the types of the galaxies. So we simply ignore them. Of course, there is much more details on how we select these clusters. They are outlined in the monography document, but basically here we just select clusters that we call prominent, that will demonstrate a more homogeneous content of the galaxies within, and we extract them from the grid. So for the next step, we will take all the galaxies that contained within these clusters and assign labels based on how Sombrero did a separation. So from the blue clusters, we end up getting spiral galaxies, and from the red clusters, we end up getting elliptical galaxies. Perfect. Before we will go to the next step, let's evaluate the accuracy that we got from these clusters. So only taking galaxies from prominent clusters and comparing with the real labels. We are getting 95% of the galaxy with a really good per class misclassification rate, which is really low. Just to remind you that Paolo Barchi was able to get 94.5% of overall accuracy using supervised method trained with metrics. We are getting 95, which is demonstration of how capable Sombrero based on the metrics is. But we have a price to pay. We lost a lot of galaxies. So we got back only 9,000 galaxies that were located in the prominent clusters. But here where we will go to the deep learning, and we will be able to compensate this loss. So basically, now we have our data set that has labels, but these labels do not come from human classification. They come from unsupervised clustering, and we are ready to train CNN model. We are using pre-trained exception architecture with weights from ImageNet, and as we are using already pre-trained weights, we need to have two steps. We need to have feature extraction and fine-tuning. How it works? So in the first step, we need to familiarize our model with new data, because previously this model was trained on data that has nothing to do with the galaxies, but it has a notion of important shapes, edge detection, and so on. So we don't want to disturb this. Let's imagine this is our model. We have input as an image and output as classification. So in the first stage, we will unlock only tiny portion of the galaxy of the model to be trained. The rest will be freeze. So weights won't be adjusted. Only last layers will be modifiable, let's say. So this will run for a couple of epochs, and then after model already familiar with our new data, we will go to the fine-tuning stage, where we will unlock a bigger portion of the model And we will fine-tune the architecture with lower learning rate to increase its performance. And basically, it will conclude the training of our model on our data. Having the model, we need to test it. So for the testing, we will be using the remainder of Dominguez-Sanchez catalog, but we are excluding 9,000 galaxies that we used for the training of the model. And as additional catalog, we will be using Galaxy Zoo, which has 250,000 galaxies with visual classification. Basically, these two catalogs come from the same source. It's SDSS telescope, but they differ on from where classification comes, because Galaxy Zoo uses visual classification from people that classified it during the project, while Dominguez-Sanchez is using machine learning classification that was based on the answers of these people for the decision for the answer tree. So it's kind of same data, but classification differs in some cases. And what are our results? With Dominguez-Sanchez, so it more than 500,000 galaxies, we are getting 85% of overall accuracy. And with Galaxy Zoo, we are getting 82% of overall accuracy. I would agree with you if you would say that this is not exactly the best result, because usually machine learning are getting 95 and higher. And yes, this is true. But important thing here that our accuracy is based on the assumption that visual classification is 100% correct, which is hardly true, because it's especially true when we try to look at the galaxies that are smaller, fainter, or more complex by its nature. And we have a data that corroborates with this argumentation. If we will plot T-type from Dominguez-Sanchez versus probability from Galaxy Zoo, so of given galaxy having a given type, so we can see that red line is a probability of a galaxy being elliptical will be higher with lower T-type. Makes sense. Blue line, probability of galaxy being spiral will be higher with a higher T-type. Also makes sense. But if we will look for to the range from -1 to 0, we can see that probability of given galaxy being one on another or another is almost the same, because this is a place where classes kind of, there's a blending of two classes, and there is simply no features that we can identify reliably to assign a given galaxy to one class or another. And to make the case worse, we can plot size of these galaxies. So dashed line now shows size of the galaxy in pixels, Petrosian radius. So this is one of the smallest galaxies of all. And this dashed line is showing magnitude. So in astronomy, when you have higher magnitude, this signifies fainter object. So this one of the faintest object. So to summarize, blending classes which do not exactly have differentiable features, faint and small galaxies. So it's almost, again, you can wake up in the morning, classify one way, you can go before you go to sleep, you will classify another way. So it's kind of unfair to compare the method with visual classification that has high probability to contain bias. That's why we remove these galaxies from the testing catalog and retest our model. So we do not retrain, we just retest on catalog without these galaxies in this range. And what are our improvements? So from Dominguez-Sanchez, we went from 85% to 88%, and with Galaxy Zoo, we went from 82 to 89. Few things to point here, which are important. Now our classification is not only higher, but now it's similar between two catalogs, indicating that there was indeed some kind of bias in the Galaxy Zoo catalog with these galaxies that made disagreement between Dominguez-Sanchez and our model in general. Right, so having demonstrated our method, we need to extend it, because With CDSS, we locked in the local universe because CDSS is not able, simply that no physical power to go to higher redshifts and see more. That's why we need to transition to Hubble, HST, Hubble Space Telescope. And for this, we prepared a catalog of 650 galaxies, so not 600,000, just 650 galaxies that have imaging from CDSS and HST. All of them are low Z and bright galaxies, and all of them have T-type and classification from Galaxy Zoo. So what we did, we ran our pipeline twice, once for CDSS and once for HST, to compare the final performance between the sources of the data, because it's the same galaxies. What we were expecting is that galaxies from HST will give us a better overall results. And we already can see that this in the metric separation, two of the metrics, as expected, demonstrated better separation with HST data. And final results as well, with CDSS, we got 76% of overall accuracy as a final one, and with HST 82. You again could note that, well, these values are quite smaller that we were getting with bigger catalog. And yes, indeed, but the keyword here is bigger, because it's important to remember that we had only 650 galaxies at the beginning. So it's quite complicated to get a prominent samples, train a model, and to apply this model. So that's why, being limited by the data, we got our final accuracy is lower, but still it's competitive. And what's important for us here is an indication that HST data not only works, but provides a better performance. And having this, we outlined our future plans with this method to go to higher Z and to use better data. So we are working with the candles data, which has more than almost 200,000 galaxies from HST. And we're trying to explore range between 0 and 2.4 of redshift to see how method will fare in these conditions. And here we have a lot of discussion about challenges and maybe challenging visual classification. Because as you saw previously, already in local universe, you have visual bias in case of complex cases. So if we will demonstrate some galaxies from high redshift, we can imagine that there is a possibility of even more biased results. So here's few samples of the galaxies that we usually see at local universe. So this is Hubble images, and all of them are super bright, well resolved. We can see a lot of details, and it's easy to classify. But if we will go to redshift around 2, we can see that these galaxies are tiny, and it's difficult to see what exactly it is. So given this, we are discussing how to approach this this problem, not exactly problem, but how to approach this, and how our method can be of contribution in the classification of the galaxies in the higher redshift ranges. So we come to the end of the presentation, and main thesis contribution, basically main contribution, is a hybrid classification method that combines unsupervised and supervised machine learning with competitive overall accuracy as the final results, and improvements to the widely used astronomical tools such as matrix calculation, cleaning, segmentation, and whole package of these things. Thank you all for the attention, and I thank you, Capis, for founding this research and making these results possible.